Hello guys, this is Camille Gamarcha, the in charge of discussion in this group.
Hello guys, I am Janelle Rosette G. Pineda, the in charge of the procedure in this group.
Hello guys, this is James Gert Aying, in charge of the table on this video.
I'm Will Rose Castellano, in charge for the analysis of this group.
Hi, I'm Dr. Paul Mayari, the in charge of the conclusion in our group.
Hi, I am Justin J. Peron and I'm in charge of the editing of this group.
In our laboratory experiment 6, we are to verify the principles that governing resistances which are connected in parallel, and the material we used is the FET simulator, the circuit instruction kit DC. We first made a parallel circuit by attaching the wires to the battery. We then attached the ammeter 1 to the wire along with a resistor and positioned it in a parallel way. After that, we attached a wire to ammeter 1 and attached ammeter 2 in it along with its resistor and positioned it also in a parallel way. We then attached more wires and connected it in the third ammeter and added a switch and more wires so that it will be connected to the battery. After finishing the circuit, we then proceeded in gathering the values needed. For R1 and R2, we just simply set our chosen values to resistor 1 and 2. For the total resistance, we just use the formula 1 over RT is equal to 1 over R1 plus 1 over R2. To get the values of I1 and I2, we just simply look in ammeter 1 and 2. And for IT, the value of it can be seen in the third ammeter. And lastly, to get the value of V1, V2, and V3, we just use the voltmeter provided.
And in the parallel, volts are in constant and will remain the same throughout the trials. In trial 1, the computation in the resistance are 1 over resistance 1 plus 1 over resistance 2, which is 1 over 30 ohms plus 1 over 40 ohms, equal to the total resistance of 0.0583 ohms. The computation in the ampere is we added each ampere to get the total, that is the 0.80 ampere plus 0.60 ampere is equal to the total of 1.40 ampere. In trial 2, the computation are the same as the trial 1, which is 1 over 50 ohms plus 1 over 60 ohms is equal to the total of resistance of 0.0367 ohms. In ampere, we added 0.48 ampere and 0.40 ampere, in which the total of 0.88 ampere. And in trial 3, the computation in the resistance are 1 over 70 ohms plus 1 over 80 ohms, in which the total resistance of 0.0268 ohms. In the ampere, we added 0.34 ampere and 0.30 ampere, which is equal to the total of 0.64 ampere.
Resistances are said to be connected in parallel when the total current divided among the voltage across each of them is equal to the voltage across the combination. For our rules, we have the first rule: the total current is equal to the sum of the separate currents, such as IT is equal to I1 plus I2 plus I3 and so on. For rule number 2, the voltages across the resistance are equal and they are also equal to the voltage across the combination. For rule number 3, when resistors are connected in parallel, the reciprocal of the joint resistance is equal to the sum of the reciprocals of the separate resistances. Lamps and other appliances in our homes are connected in parallel, the common voltage being the line voltage, either 110 volts or 220 volts. The principal advantage of this arrangement is that there is a separate control for each lamp or appliance. Putting on any lamp in the house means inserting one more branch in the parallel combination. Sometimes, when the house is far from the source of power, the lamps grow dim whenever a toaster, an electric iron, or any other powerful appliance is turned on. When the appliance is turned on, the current passing through the line is increased. This large drop in the line of voltage decreases the voltage available at the entrance to the house, and hence the lights dims. This is the table for our data. In trial number 1, we have resistance 130 ohms, resistance 240 ohms, and the total resistance is 0.0583 ohms. Current 1 0.80 amperes, current 2 0.60 amperes, and the total current is 1.40 amperes. For voltage 1, 24 volts, voltage 2, 24 volts, and the total voltage is also 24 volts. For trial number 2, resistance 1 is equal to 50 ohms, resistance 2 60 ohms, the total resistance is 0.0367 ohms. For current 1, 0.48 ampere, for current 2, 0.40 amperes, and for the total current, 0.88 amperes. For voltage 1, we have 24.0 volts, voltage 2, 24.0 volts, and the total voltage is 24.0 volts. For trial number 3, we have resistance 170 ohms, resistance 280 ohms, and the total resistance is 0.0268 ohms. For current 1, we have 0.34 ampere, for current 2, 0.30 amperes, and for the total current, 0.64 amperes. For voltage 1, we have 24.0 volts, for voltage 2, 24.0 volts, and for the total voltage, also 24.0 volts.
For our analysis, we are given 3 sets of data with 3 trials in one table. The given data are divided into resistance, current, and voltage. As shown on the table, the values for the resistance, both the R sub 1 and R sub 2, are lined up from the lowest to highest, making the total resistance higher. The same thing happened in the current. The relationship between resistance and current are inversely proportional. In other words, if we increase the resistance, then the current will decrease, while the voltage and current are directly proportional, and the total voltage remain constant.
Therefore, we conclude that the values of the resistance, both the R1 and R2, are lined up from the lowest to the highest, making the total resistance higher. In the case of the current, the relationship between resistance and current is inversely proportional, meaning that if we increase the resistance, the current would decrease, while voltage and current are directly proportional.